So let's see matrix decomposition. What is matrix decomposition and what are different types of matrix decomposition techniques available to us. So this is one mind map which explains how the eigenvalue, eigenvectors and determinant are used in different concepts of machine learning. If you see here, I'm calculating determinant. Why I did determinant? Because if I want to find out eigenvalue, we studied yesterday that a minus lambda I modulo equal to 0. This is what determinant. So determinant is using eigenvalue. Where we need eigenvalue to calculate eigenvectors, I need eigenvalues. That also we have seen how to calculate eigenvalue, and for each eigenvalue, how to calculate eigenvector. Once I calculate eigenvector, I can use those eigenvectors in dimensionality reduction. How? That I have already told you how we are using that in PCA, in principal component analysis, or in dimensionality reduction. How are we using eigenvectors? Why I need eigenvectors? I need eigenvectors to form the covariance matrix. Covariance matrix. Once I form the covariance matrix, I can apply principal component analysis techniques on that. Then using this, I am achieving dimensionality reduction. So that way, eigenvalue, eigenvectors or determinant is indirectly used in dimensionality reduction of machine learning. Okay, and eigenvalues are also used in diagonalization. We'll see this diagonalization. What is diagonalization? And this concept is used in SVD. The most important matrix decomposition technique, which has wide applications, is singular value decomposition. Singular value decomposition. This is one technique which is used very widely in top machine learning algorithms, and it has wide applications on image processing, maybe image compression, image denoising. For a lot of related image processing related tasks, we use this SVD algorithm. SVD has a filter. In advanced Python libraries, we have directly an SVD filter, which is used as a step before processing any image. Okay, so that way we will be using it. Also, I use determinant to check whether it is invertible or not. If a matrix is inversible, then we do Cholesky decomposition. Why we need Cholesky decomposition? This is another decomposition technique. Cholesky decomposition, it is used in probability and distributions, right? So this is one mind map which explains how and where the eigenvalues are used in decompositions techniques specially. Also, here you can see different applications of this matrix decomposition techniques, right? What are the different methods available in matrix decomposition? Eigen decomposition, singular value decomposition, LZ, Cholesky, and there are a lot more. Okay, so we are going to see few of these decomposition techniques. And where are these matrix decomposition techniques used? If you see PCA, principal component analysis, SVD. Again, here it is same. SVD is, I'm telling you, SVD has a separate filter which is used in image processing. So there also we use this. So PCA uses this decomposition techniques. SVD or image processing uses this SVD technique, right? So this is about matrix decomposition. Again, what we can do matrix, this is just basic things about that, and it has a lot of applications as well. Okay, so this is one which gives an idea or the importance of matrix decomposition. So why we have to do matrix decomposition, right? See, I have a big matrix with me. Again, I will talk a little about image processing here. I told you before that an image is a collection of pixels. Image is a collection of pixels, and each pixel is a 3 by 3 matrix. Pixel is like a dot. So each pixel is a 3 by 3 matrix. Similarly, an image has some lakhs of pixels. So you have a huge matrix with you. You have a huge matrix with you, right? Working on such huge matrix is difficult. Loading the matrix, doing some operation, maybe calculating determinant, calculating eigenvalue, eigen decomposition is difficult. So what we do, we try to decompose, we try to break down the matrix. It is sometimes called as matrix factorization. You might have studied this factorization. Simple, if I want to write 10, what I'm doing, I'm representing it as 2 into 5. I'm finding out the factors of that number 10, and I'm expressing that number into this form. Why? When I express this, it becomes simple, and it is easy for calculations. Sometimes in big problems, This is a simple one, but I think somebody is working on cyber security. They might be knowing in cryptography algorithms that a number, given a number, it has to be expressed as product of primes. Product of primes. So 21 can be expressed as 7 into 3 prime numbers, right? So it is required sometimes to represent a given number into its multiplication of its factors. So what is happening here? See, the value is same, 21 and 21. Only thing, we are breaking down and expressing it in different forms. So same thing is matrix decomposition. What we do, we break down the matrix into different representations. We are not changing its value, its property, its originality, what it is representing is not being changed. It is intact. Only thing, we are just decomposing them into parts. Why are we doing that? Because we are having complex matrix, and such a huge complex matrix, I cannot apply my operations. It is time taking, or it is little difficult to do. So we are trying to express a given matrix into some set of separate matrix. Best example I can tell you, that's we are going to see anyhow. If I have a matrix A, I am representing it as multiplication of L into L transpose. So L is a triangular matrix. So if I have a matrix A, I am representing it into two different. This is one way of matrix decomposition. If you multiply both, you get answer A again. But why am I doing this? Applying operations on A is difficult, but applying on L and L transpose is easy. So having two separate matrices, playing with those two separate matrices is easy. But the original matrix is not going anywhere. It is intact. That is the main idea behind matrix decomposition. It has lot of applications, and there are different kinds of matrix decomposition techniques, right? So application of matrix decomposition, I have said, right? Image compression, image denoising. See, there exists a SVD non-linear filter. If you are using some machine image processing libraries, we have this SVD non-linear filter with us, and recommender systems collaborative filtering. Example of image compression, what is this? You are attending a online meeting with your video on, right? When the video is on, image compression is how what it happens is there. See, you can see me, my face alone is the major focus part, which has to be present nicely. So during image compression, when I am switching on my video, it requires more data to have to show you this video, right? So what internally it does is, this particular software Cisco, it does some image compression. Only it focuses that particular. So if this is the picture or the video which you see, somewhere my face is here, something like this. The remaining part here is not of that importance, right? So what it does, image compression, these particular parts are ignored. So only this part is focused more. So what you are trying to do here, we are decomposing. Say again, this image is a matrix. In that matrix, we are trying to break down that image into different matrices, which the one which has more importance is intact, remaining all is removed. Okay, so it also requires some matrix decomposition techniques. Image denoising, also same. You want to remove some irrelevant information from the images. Simple example, maybe you might have studied about sparse matrix, which has more zeros and less numbers. Something like this. This can be called as sparse matrix, sparse and dense matrix. So sparse matrix means it has more zeros here, right? So I want to remove these zeros. The features which are very important are here only. Remaining part are not required. So we try to decompose this into, if I can decompose this into two separate matrices, maybe one with all zeros, other one with all numbers. If I can do, for example, then the other one I can ignore. I can have the important features in one matrix. There I can apply my operation and do some operations, right? That way it is also used in image denoising. Recommender systems, if generally, we get lot of recommendations. If you are searching something based on the previous search history, it shows you the recommendations. So there also we use collaborative filtering, is one technique in machine learning. It's a important technique in machine learning. It uses SVD decomposition, singular value decomposition, in its algorithm. Okay, so this three things are major applications, but it's very clear that matrix decompositions are having wide applications in machine learning and deep learning algorithms. So what are those decompositions? See, so different kinds of decompositions exist. So one is Cholesky decomposition, other one is eigenvalue decomposition, the third one is singular value decomposition. These three are very, very popular techniques which are widely used. So today we are going to study these three things. Like I said, though we are doing a lot of mathematics, finding out eigenvalue, eigenvector, we are calculating it. In Python, it's very, very easy. Just one click, it gets the answer. So let us see all three of them, how to do it mathematically, and also we'll see how it is done in Python programming, right? So the main agenda was that to understand the underlying mathematics. So I hope it's clear. Matrix decomposition is simple technique where we are trying to break down the original matrix into two or three different matrices without losing its original property. Why are we breaking down? Once you break it down, doing some operations on those sub matrices is very easy instead of doing operations on complex matrices. So among them, the first technique is Cholesky decomposition. So this is the name of the fellow who proposed it, Cholesky decomposition, also called as Cholesky factorization. Sometimes matrix decomposition is called as matrix factorization as well. So what is this? Consider a symmetric positive definite matrix. I'll talk what is this positive definite matrix. Consider a symmetric positive definite matrix. Suppose like this A, if it has elements like this, it can be decomposed into two separate matrices, L into L transpose. Like this, you see L11, 0, 0, L21, L22, 0, and its transpose. I can break a matrix of this form into these two forms. So it means if I can find out this L matrix, that's it. I can say that this is represented as product of two numbers. Simply like this, like I told, 21 is represented as 7 into 3. So I want to represent this number 21 into two separate prime numbers. Product of two separate prime numbers. So that similar kind of application. So, sorry. So this is the one technique, Cholesky decomposition. Let's see how it is done. So given a matrix A, if you can decompose like this, what are the benefits of doing this? See, this L is called the Cholesky factor. L is called the Cholesky factor. What is the benefit you see? If I want to calculate the determinant of this matrix, it is nothing but the product of these three. Simple, I can easily do this, right? And since the majority here are via zeros, right, it is easy for us to make some insights, draw some insights from these matrices. Okay, so this is used more in probability distributions. We'll come to that. I will when we discuss the next concept, that is probability, the second part of the course of this essential mathematics. There I will talk about this decomposition, which helps us. Now I don't want to go into probability. We have to study a lot of probability and its distributions, and then we'll see how and where it is used. Right? So it's simple. Now, how to find out this? Somebody gives you this matrix A and asks you to represent this matrix using Cholesky decomposition as two separate matrices. Okay, so see, you have to multiply these two. If you multiply these two matrices, you get a matrix like this. Right? You get a matrix like this. L11 into L11, L11 square, plus 0 into 0, plus 0 into 0. So nothing changed. Next, L11 into L21, plus 0, plus 0. So now change. L11 into L31, then 0 into this, then 0 into this. So L31, L11. This way, if you multiply these two matrices, you get this. Indirectly, it means, you see, what is the value of A11? Now, see, your target is given a matrix A, find out, represent that matrix into two separate matrices, L, L transpose. So I have to find out L first, that's it. How to find L? L has terms 1, 2, 3, 4, 5, 6. It has 6 terms. So I multiplied it, I got this. From this, I can say L11 value, reverse, you see, I have matrix A here. So L11 is equal to A11. So L11 square equal to A11 means L11 value is nothing but square root of A11. L11 is nothing but square root of A11. Right? What is A21 value? So I can write here L21, L11 equal to A21. I want L21 value. L21 equal to A21 by, I know what is L11 value. What is L11 value? Square root of square root of A11. That way, by equating these two matrices, you can find out the values of L11, L21, L22, L31, 32, 33. Once you get this, it is easy to represent them, right? So let us see one example and try to find out. I hope it is clear. We will be referring to these equations because from this it is easy to calculate. I hope you understood. Cholesky factorization is one technique where we are trying to decompose a given matrix into two submatrices. Okay, where each of them are transposed to each other. Each of them are transposed to each other. So if you want to find out determinant of A, you have to simply find out determinant of L. If you multiply these two, you get the value, right? So this is one technique of decomposition. This is also widely used. Let us take a numerical problem, try to solve it. But before going to that, let us study what is a symmetric positive definite matrix. To apply Cholesky decomposition, that matrix should be a symmetric positive definite matrix. So what is a symmetric positive definite matrix? Let us see. Okay, a given matrix A is called as symmetric positive definite matrix if X transpose A into X is always greater than 0 for any given value of X. For any value of X. If a given matrix A, it can be called as a symmetric positive definite matrix if X transpose A into X is always greater than 0 for any given value of X. Let's take an example. Let me take value A as a matrix 9, 6, 6, 5. When you call a matrix as symmetric, if A equal to A transpose, A equal to A transpose, we say it is symmetric. Yes, this is symmetric. Now, let's try to do this. X transpose A into X. So, since it is 2 cross 2 matrix, I will take my X as X1, X2 into this 9, 6, 6, 5 into I will take this X1, X2. Okay. This is since A transpose, I'll take a vector. So, I will have here X1, X2 and this one as X1, X2. Now let us multiply this. If you multiply this, if you do this operation, X1 9, so 9 X1, this is 1 cross 2, this is 2 cross 2. So we get 1 cross 2 as the value. So 9x1 plus 6x2 is one value. Then 6x1 plus 5x2 is 1. Then you have x1, x2. If you multiply this, you get some big equation here. Let me write it here. You can write. So it is 9x1 square plus 6x1 x2. This becomes one value, right? This into this plus this into second term. So 6x1 square plus 5x1 x2. This thing I have to multiply with this. This thing I have to multiply with x2. So not sorry. Here it is x2. x1, x2 and 5x2 square. Right? So if you add this, I think you get something here. 13x1, x2, 12, right? So I get here 9x1 square plus 12x1, x2 plus 5x2 square. For given any values of x1, x2, it should be always greater than 0. This should be always greater than 0. So maybe I think I can express this as something like this: 3x1 plus 2x2 whole square plus x2 square. If you convert this into operations, you get this. Now you see, both are squares. In a bracket, I have square plus x2 square. You give any value, x1, x2, minus, plus, 0, anything. It's always greater than 0. Not 0, sorry, minus values or positive values. It's always greater than 0. Therefore, I can say this given matrix is symmetric positive definite matrix. You can apply Cholesky decomposition only if it is a symmetric positive definite matrix. I know one of my students attended the interview for a deep learning or ML position. There they asked him about this symmetric positive definite matrix. Okay, if you given matrix A can be called as symmetric positive definite matrix if x transpose into A into x is always greater than 0 for any given values of x and x1 and x2, right? So that way it can be called as symmetric positive definite matrix. If you take one more example which is not something 9663, if I take 9663. Okay, so if I again solve this, I may get an equation something like this: 3x1 plus 2x2 whole square minus x2 square. So this cannot be greater than 0 when I take x1 value as 2 and x2 value as minus 3. If I take these two values, this equation is less than 0. See, 326 minus 2 into minus 3, 6 whole square minus 3 whole square. So 0 minus, this is 9. So minus 9 is not greater than 0. Therefore, for these two given values, this matrix is not a symmetric positive definite matrix. Clear? Now let's go and apply our Cholesky decomposition. Given a, let us take an example how we try to solve that. So given a matrix A, I request all of you please solve this, because in Python programming it's very easy, but you should know how it is calculated manually. So you have a matrix 4, 12 minus 16, then 12, 37 minus 43 minus 16 minus 43 and 98. I have a matrix like this. Check whether it is a symmetric positive definite matrix or not. Okay, so assume it is a symmetric positive definite matrix. Assume it is already done. If you can calculate, you can still do it, and you can see this is symmetric because A transpose is equal to A. Now, how to find out this? We already know how to calculate it. So let us go here. In this diagram, we have seen that A value, A11 value is nothing but L11 square. So if I want to find out the value of L11 is nothing but square root of A11. So L11 value is nothing but square root of 4, that is 2. Next, come here. From this, A21 is nothing but L21, L11. A21 is nothing but L21, L11. So L21 can be written as A21 by L11. L21 is nothing but A21 by L11. A21 by L11, that is L21. Now what is A21 value? A21 is this 12. Yes, A21 value is 12. So 12 divided by L11 is 2. So it is 6. So we are trying to fill the matrix. So here it is 2, 0, 0. Here it is, what is this? L21. L21 is this. So L21 is 6. Now we have to find out the third value, that is A31 and L31 we have to find out. So L31 is nothing but A31 by L11. A31 by L11. So A31 by L11. So what is A31? A31 is minus 16. Minus 16 by L11 is 2, that is minus 8. So this value is minus 8. Right? Next, go back. Now we have to find out L22. L22 means L22 is nothing but no, A22. A21 is done. We have to find out, if you see here, yeah, we need to find out these 3 over. Now L22. L22 means this term here. So what is that term here? I'll just quickly erase this. We want L22. So L22 square plus L21 square is nothing but A22. From this, L22 square equal to A22 minus L21 square. So what is A22 value? A22 value from the matrix is 37. So 37 minus L21 square. So what is L21 value? Is 6. L21 value is 6. 6 square. This is square root. So 37 minus 36 square root is 1. So this value is 1. Okay. So we find out next. Next what we have to find out? We need to find out L32 means this term. Because I have L32 here. So A32 is equal to this, where I have L32. So I can write A32 equal to L31, L21 plus L33, L22. So you know A32 value. What is from this matrix A23 values? Minus 43. So minus 43 equal to L31, L21. So these two, 6 into minus 8. So minus 48 plus L33, L22. So L22 is 1. So L33, uh, L33, L32, sorry, L32. Now, you solve this, you bring this 48 this side, L32 becomes 5. This is 5. This is anyhow 0. Only last term we have to find out. What is the last term? L33 we have to find out. So L33 is available in this. Right? So how to find out L33? L31 square, that is this square plus this square plus this. So we know from here that minus 8, let's erase this, right? So minus 8 whole square plus 5 square plus L33 whole square equal to, from this is equal to A33, right? A33. A33. So from the matrix A33 is 98. So this 8 square 64 plus 25 plus L33 square equal to 98. So this is around 89. So L33 square equal to 98 minus 89. So it is 9. So L33 becomes 3. You got this 3. So this is your L matrix. This is your L matrix. Now L transpose is just writing transpose of it. So how do I do the transpose? We got the L matrix. Now you have to represent as L transpose of it. So just make it rows into columns and columns into rows. If I write that way, so it becomes 2 0 0 6 1 0 minus 8 5 3. So this is L, this is L transpose. We are able to represent this matrix A into L into L transpose. This is Cholesky decomposition. If you multiply this, still you get this matrix as the original. So your original matrix stays same. You will not have any difference. You get the same answer, right? So this is Cholesky decomposition. I hope you understood. It's a simple way. There are multiple ways of representing a matrix into different forms. I can represent into L transpose. I can represent A into maybe some Q, D, Q inverse. I can represent A into some U epsilon, V transpose. There are multiple ways. These are different techniques, decomposition techniques. Why am I representing it? We already studied that having a complex matrix, doing operation on that complex matrix is difficult. For that purpose, we are trying to convert that into decompose that matrix into different small matrices. Like we do number factorization, we are doing matrix factorization. So having such matrices, it is easy for me to do the operations instead of doing that in complex matrix like this. You can see your small numbers here. You can calculate, do all things, whatever you want to do. And finally, you can have the original matrix. This has wide application in image processing especially. So this is an example of Cholesky decomposition. Any doubts in this? Otherwise, we will move to the next decomposition technique, that is eigenvalue decomposition. Any doubts? Any queries you have in this decomposition techniques? We also have to see our Python implementation for this. Sorry. Eigenvalue decomposition. So let's understand what is this eigenvalue decomposition. Let's talk about diagonalizable. Sorry, let's go back. Yeah, if you see here, we are having This is what we are doing for Cholesky, but when you are applying eigenvalue decomposition, it's not given in this graph, but we have to find out whether it is diagonalizable or not. Okay, so if it is diagonalizable, then only we can apply SVD or eigenvalue decomposition. These two are different techniques. So when can you say a matrix is diagonalizable? Okay, so for this example, you have given a matrix. If you have a matrix 2 by 2, 2 cross 2 matrix, you have to find out eigenvalue. See, if the size of the matrix is 2 cross 2 or n cross n, then I should have n eigenvalues. I should have n eigenvalues. Only then we say that the particular matrix is diagonalizable. For example, suppose you have a 3 by 3 matrix and you get only 2 eigenvalues. And if you get only 2 eigenvalues, such matrices are not diagonalizable. Condition 1. Condition 2, you have a 2 by 2 matrix or n cross n matrix. All the eigenvalues should be real. They should not be complex numbers. They should not be complex numbers. Only then such matrix are called diagonalizable matrix. This is a precondition. Like for Cholesky decomposition, I said that symmetric positive definite matrix is required. Same way, for eigenvalue decomposition, the matrix should be diagonalizable. Only the diagonalizable means trying to convert that matrix. What does it means? You have a matrix A. If you can express this matrix A into 2 or 3 submatrices, okay, right? So I should be able to represent the properties of this matrix A in diagonal elements. It means I can have some matrix like this where I have 1 0 0 0 2 0 0 0 3 this way. So I have a diagonal. So I should be able to represent a matrix A into different matrices where at least one matrix is having only diagonal elements. That is possible only when you have real eigenvalues. And if the dimension of the matrix is 2 cross 2, then you should have n eigenvalues. This is the property diagonalizable. Let's see an example whether the given matrix is diagonalizable or not. See, here I have a matrix A. I'll take 3 minus 1, 1, 5. Let's find out its eigenvalues and see whether it is diagonalizable or not. If I calculate A minus lambda I for finding out eigenvalues, I have to do A minus lambda I modulo equal to 0. So 3 minus lambda minus 1, 1, 5 minus lambda. If I multiply this, 3 minus lambda into 5 minus lambda minus into this 2, if I multiply, it is minus 1. So this become plus 1 equal to 0. So if I can see, I get maybe 315 minus 5 lambda minus 3, that is 8 lambda plus lambda square plus 1 equal to 0. So it is lambda square minus 8 lambda plus 16 equal to 0. So there is no way I can express this. So I have to go for, if I find it out, I can see that the lambda values are not real numbers. They are complex numbers. If you apply minus b plus or minus square root of b square minus 4ac by 2a, if you do this, you get complex numbers here. I cannot find out its factors directly, right? So the lambda values are complex. So this is not diagonalizable matrix. To apply eigenvalue decomposition, that matrix should be diagonalizable. First condition we understood. Now how do we solve this eigenvalue decomposition? What are those? How do we? If you remember Cholesky decomposition, there we were expressing a matrix A into two matrices L into L transpose. Here in eigenvalue decomposition, we are expressing a matrix A into P, D and P inverse. We are expressing it as product of three matrices: P matrix, D matrix and P inverse is just inverse of this, inverse of a matrix. Okay, so what is this D? D is diagonal matrix. D is diagonal matrix. Okay, so how is this? What is the procedure of eigenvalue decomposition? Let us avoid confusion. Let us erase this. So how do you find out this PD, P inverse. So D matrix is nothing but, suppose, assume A is a 3 by 3 matrix. So we are assuming that it is diagonalizable. So I may have 3 eigenvalues. What are those? Lambda 1, lambda 2, lambda 3. So D matrix is nothing but just keep those eigenvalues in order. So lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. This is your D matrix. Just simple set. So for A, you find out eigenvalues. Those eigenvalues you put in diagonal order. This forms your D matrix. This is done. Now what is P matrix? P matrix is formed by calculating, okay, I want to calculate eigenvector for each eigenvalue. So eigenvector of lambda 1, I may have x1, x2, x3 for example. Similarly, eigenvector for lambda 2, I may have y1, y2, y3, another vector. Similarly, eigenvector for lambda 3, that is each eigenvalue has eigenvector, right? So z1, z2, z3. This way I have 3. P matrix is formed by combining these 3 eigenvectors. So x1, x2, x3, y1, y2, y3, z1, z2, z3. So you know how to calculate D matrix, you know how to calculate P matrix. How we got this P matrix? It is nothing but the combination of 3 different eigenvectors of those 3 eigenvalues. Okay. Now what is P inverse? You have to find out inverse of this matrix. If you can find out inverse of this matrix, your job is done. How to find out inverse of this matrix? You can apply reduced row echelon form. You can make an augmented matrix AI and convert this into reduced row echelon form, complete matrix. You get the inverse. So that way you can find out D, P and P inverse. This is eigenvalue decomposition, right? So maybe you can spend time, try to solve a problem in finding out. I'll just quickly summarize the important point here. So eigenvalue decomposition representing a matrix into product of 3 different matrices P into D into P inverse, where D is a diagonal matrix. Say diagonal matrix. How do you form this diagonal matrix? Matrix A, which is of size n cross n, will definitely have n eigenvalues. Let it be lambda 1, lambda 2, so on, lambda n. For 3 by 3 matrix, we have 3 eigenvalues. So your D matrix looks something like this. Lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. Now we want to form P matrix. P matrix is nothing but the corresponding eigenvectors for those eigenvalues. So for lambda 1, it is x1, x2, x3. For it is y1, y2, y3, z1, z2, z3. So you have 3 eigenvectors. Find out its inverse. You can find out P inverse. Write them as a product. If you write them as a product of these 3, this becomes eigenvalue decomposition. So we are able to convert this matrix, decompose that matrix into product of 3 separate matrices, where one matrix in the middle is a diagonal matrix. Okay. One very important condition is that you can ask me, sir, when I calculate eigenvalues, for me, for this matrix A, when I calculate eigenvalues, I got eigenvalues as 3, 1, 0. For example, your friend calculated, he got eigenvalues as 1, 3, 0. Okay, they're in different order. Because equation solving, I can write lambda equal to 2, 3 or 3, 2. Anything I can write. So in which order should we write here? When you are forming this diagonal matrix, whichever order you take, it is your choice. Whichever order you take these eigenvalues, suppose you are including D matrix like this. I know that the eigenvalues are only 0, 1 and 3. So which order should I take? You take any order of your choice. Suppose I want to take first 1, 0, 0, then 0, 0, 0, 0, 0, 3. I am taking the order 1, 0 and 3. Similarly, when you are forming this P matrix, you have to make sure that the eigenvalue 1's eigenvector should come in the first place here. Eigenvector of this eigenvalue 0 should come here, and eigenvector of this eigenvalue 3 should come here. So the order in which D matrix is formed, in the same order P matrix should be formed. That is one very important condition. But as a standard, in most of the books they have written that it is best practice always to have this in decreasing order. It means if the eigenvalues are 310 or 130 or 103, whatever, write them in decreasing order. So 3 should come first, then should come 1, then should come 0. There is nothing wrong in taking any order, but the standard recommended is to put them in decreasing order. Okay, eigenvalue decomposition. Right. So next one, the third decomposition technique, we will see this using Python programming. It's a single one-step program. You load the matrix, you simply use this linear algebra package which is there in NumPy, and you can just give here SVD. If you're using SVD, you can give SVD of matrix A. That's it. It gives you the decomposition matrices. If you want to give Cholesky decomposition, we know that Cholesky generates a matrix L. So you can give L equal to np dot linear algebra dot Cholesky of matrix A. That's it. It will give L. You got L, you find out L transpose over. That is the product of two matrices. Okay, so like this we have functions which can help us in Python programming. Let's see the third one, singular value decomposition. Very popular, singular value decomposition. This is very widely used in image processing, especially I will say in AI or ML or deep learning algorithms. What is this singular value decomposition? Again, we are studying decomposition techniques or factorization techniques where we are trying to express a matrix A into product of some few matrices, maybe product of 2, maybe product of 3, or so on. So in singular value decomposition, given a matrix A, it can be expressed as product of a matrix U, sigma, and V transpose. We are trying to express a matrix A into product of three different matrices, U, sigma, V transpose. What is this U? What is this sigma? What is this V transpose? Let us see. Okay, so first thing about size. Suppose this matrix A, why are we studying singular value decomposition? Why can't we apply eigenvalue or Cholesky decomposition? Okay, you may ask me, sir, eigenvalue decomposition, in eigenvalue decomposition also, I am trying to express this into three matrices, no? P, D, P inverse. I am able to express into three matrices, right? Here also I am doing three matrices. Why we need singular value decomposition? The point here is that eigenvalue decomposition is applicable only for square matrices. If it's a perfect square matrix n cross n, only then you can apply eigenvalue decomposition. Whereas singular value decomposition is a technique which can be applied for any matrices, rectangular matrices, 2 cross 3, 3 cross 2, 2 cross 3, any matrices. Whether it is square or not square, we can still apply singular value decomposition. Whereas eigenvalue decomposition, we can apply only for square matrices. That is one very important point. We are studying singular value decomposition, and not always the matrix what we are having is in same size. So assume that size of A is m cross n. Size, assume, because I am taking, see, you can apply singular value decomposition SVD even for square matrix. Even if it is not square, still we can apply. So given a matrix A of size m cross n, then I can express this U as m cross m, epsilon as n cross n, and V, sorry, this is m cross n. This is m cross n and this is n cross n. This way. So U should be, for example, if A is given as for us 3 into 2, then U matrix will be 3 cross 3 into epsilon matrix will be original 3 cross 2 and V matrix will be 2 cross 2. Okay, this is the size of matrix if they are not rectangular. If it is square, it's fine. Everything, if this is 2 cross 2, this is 2 cross 2, this is 2 cross 2, this is 2 cross 2. Okay, so let us see how to solve a given matrix, how to decompose a given matrix using SVD technique into two separate matrices. Let's take an example to understand this better. I'll take a small matrix for easy understanding. So we have a matrix 2, 2, minus 1, 1. I want to decompose this matrix using SVD technique into three separate matrices. So the first step here is to find out A transpose into A. Find out A transpose into A. So how do you find out A transpose into A? So I will take A transpose, that is 2, 2 minus 1, 1 into original A, that is 2, 2 minus 1, 1. If I multiply these two, I may get a matrix something 3, sorry, I'm directly writing it because you can multiply those and see 5, 3, 3, 5. Okay, so I got a matrix A into A transpose, let it is called B as B matrix. I got a original matrix B. That is the first step. First step is to multiply A transpose into A. So you get a matrix B like this. Now, once you get this matrix, your job is to find out, yeah, we were talking about A, this, right? A can be expressed as U, epsilon and V transpose. So here also the first step is that for B matrix which is formed here, find out eigenvalues. Let it be lambda 1, lambda 2 because it's a 2 by 2 matrix. I'll take a small example, lambda 1, lambda 2. So your epsilon matrix will be, your sigma matrix will be nothing but square root of lambda 1, 0, 0, square root of lambda 2. Okay, your epsilon matrix will be square root of lambda 1, 0, 0, square root of lambda 2. That is done. Now, what is this V matrix? V matrix is nothing but your normalized eigenvectors. Means you find out eigenvector for lambda 1. Eigenvector for lambda 1 can be x1, x2. Eigenvector for lambda 2 can be y1, y2. This you have to normalize it. Normalizing eigenvector means, suppose I have an eigenvector x1, x2. I have a vector v equal to x1, x2. Normalizing this vector means, normalized form of vector v means x1 by square root of x1 square plus x2 square. Next, x2 by square root of x1 square plus x2 square. This is the normalized vector. We do normalization here for this vector x1, x2 by doing this. So you have to normalize these two vectors x1, x2, y1, y2. These are two separate vectors, right? Normalize them, then do transpose of that. Include it here. So you understood what is epsilon sigma matrix is nothing but square root of lambda 1, 0, 0, square root of lambda 2. And V matrix is nothing but, V is nothing but the normalized vectors of lambda 1 eigenvector and lambda 2 eigenvector. Now, the third one is U. Let's see what is U matrix. That is little complex to understand. See, your U, again it says 2 cross 2, right? Because for this, so U is nothing but you have to find out two vectors U1, U2. You have to find out two vectors U1, U2. So U1 is nothing but 1 by square root of lambda 1 into given matrix A into lambda 1's eigenvector, that is V1. That is V1, right? If you multiply these three, you get your U1. What is U2? 1 by square root of lambda 2 into the original matrix A into the vector V2. The vector V2. This is your U1, U2. This way you can calculate U1, U2. So you get a U matrix, you get a sigma matrix, you get V transpose. That way we are trying to express them into three separate matrices. So for this problem, let us solve. I'll quickly give the direct steps so that once you watch the video and try to solve it numerically, this may be helpful for you. SVD is very, very important. You can read research papers also. You can find that SVD technique is applied at some of the steps in image processing papers. They will talk about SVD filter. They'll talk about the step of SVD decomposition, the original using SVD they will say. Okay, so let's try to solve. If I can solve this, I will quickly directly write the steps because I have already solved this. So you have this B matrix. For this B matrix, you are finding out eigenvalues. So eigenvalues, if you solve, you get lambda 1 equal to 2, lambda 2 equal to 8. Now, you got eigenvalue, you find out eigenvectors for each of them. Eigenvectors for lambda 1, eigenvector is nothing but I think it is 1, 1. Minus 1, minus 1, 1 is the eigenvector for 2. How to normalize this? So this is my V1. This is my V1, vector 1. How to normalize this? Normalized vector V1 is nothing but minus 1 divided by So what is this? Square root of x1 square plus x2 square. So square root of minus 1 whole square is 1 plus 1 whole square is 1. So square root of t. So square root of 2, 1 by square root of 2. This is my normalized vector v1. Next, you have vector v2. You are finding out eigenvector for 8. If you solve, you get eigenvector as 1 1. If you normalize this v2, you get something like 1 by square root of 2, 1 by square root of 2. So you form the v matrix now. So you got sigma matrix, you got v matrix. How? What is that sigma matrix? Let's see. Here the condition is that you should write everything in decreasing order, definitely. That is the precondition here. That's what we are saying, no? The best practice is to write those eigenvalues into decreasing order. So I form my matrix like this, square root of lambda 1, right? So square root of 8, 0, 0, square root of 2. This is my over. Now V matrix is nothing but normalized of, this is of 8, no? So 1 by square root of 2, 1 by square root of 2, minus 1 by square root of 2, 1 by square root of 2, whole transpose. This is my V matrix. Okay, so transpose you can include it later, but you find out the V matrix. So you got epsilon, you got V. Now the target is to find out U matrix. How do you find out U matrix? So we said that U matrix is nothing but 1 by square root of lambda 1 into A into the corresponding vector of lambda 1, right? So what is this 1 by square root of lambda 1? That is 2 root 2, because square root of 8 is 2 root 2 into the original matrix is 2, 2 minus 1, 1 into V vector lambda 1 is this 1 by square root of 2 and 1 by square root of 2. If you multiply this, if you multiply these two first, 1 by 2 root 2 into, if you multiply these, so 2 into 1 by root 2 plus 2 into 1 by root 2. So it is 4 by root 2, so 2 root 2. Correct. 2 into this plus 2 into this. Yes, 2 into 1 by root 2 plus 2 into 1 by root 2, 2 root 2. Then minus 1 into 1 by root 2 minus 1 by root 2 plus, so this becomes 0. So this is nothing but 1, 0. Because if I divide this 2 root 2 by 2 root 2, it is 1. 0 by 2 root 2 is 0. So 1 by 1 and 0. So your u1 term is 1, 0. You got this. Similarly, you have to find out u2. u2 means here it will be this and here it will be, I think, minus. Yes. So if you try to solve, let us see what we get. So 2 into minus square 1, or this plus this. So this becomes 0, minus into 1 plus. So this becomes 2 root 2. So this becomes, I think, 0 and 2. 0 and 2. Correct. This is 0 and 2. So we got u1 and u2 term. So you got epsilon, you got v, you got u matrix. So u matrix is nothing but your previous case it was 1, 0. Now it is 0, 2. This is your u. It means a matrix A can be represented as a multiplication of u, epsilon and v. So this is your singular value decomposition. I hope you understood. I'll quickly repeat the steps of SVD. In SVD, we express a matrix into 3 different matrices: U matrix into epsilon matrix into V transpose. The order of this should be, if it is a M cross N matrix, this should be M cross M. This should be M cross N, the original format, and this should be N cross N. Okay. For example, if you take a matrix of size 3 cross 2, then U will be 3 cross 3 into sigma will be 3 cross 2 into V transpose will be 2 cross 2. Okay. How do you form this sigma? This is nothing but your square root of lambda 1, 0, 0, square root of lambda 2, and so on. And how you form this V? V matrix is formed by considering the normalized eigenvectors of these two eigenvalues. And how you form this U matrix? U, we have already seen 1 by that lambda 1, square root of lambda 1 into the original matrix into the normalized vector 1 of lambda 1. This way you can express a given matrix A into 3 separate matrices. So this marks our eigenvalue decomposition concept.